Okay, so good morning, everybody. So we had a question already, and it looks like I might have messed up on the homework due dates, so let's see what we got here. Apparently it said Friday, October 2nd, and that's Wednesday, and okay, so I'm going to go ahead and change this at least till this Friday. And let's go ahead and check Canvas and see if I've got that set up correctly. Assignments. Oh, was that homework 3? Oh, homework 4. Okay. Due October 2nd. Okay. I'm looking for the due date here. Yep. So let's go ahead because I make mistakes like little stuff like that all the time. So, but seeing how it did say Friday and there was that confusion, let's go ahead and fix that also, and then we'll get going. Okay. So change that to the 4th. And then we just have to upload it, and then we'll be all set. EML6281, and then we're going to go down to pages and homework. And let's see if it updated. So we're going to go back to our assignments, hit update. Yay. So I'm going to pretend that never happened, but yeah, it was my mistake. So we'll make that for Friday because there's no need to have to rush that for today. Okay, so with that, it kind of feels like in the class that we need to have a breather anyway because we had a freaking hurricane, and then we had an exam, and then you got these homeworks due and everything else. And so I feel like we sort of need to reset a little bit and get back on track and whatever. So personally, like I'm just up here taking a deep breath today and just saying, oh, life is good. We'll start fresh and get going again. But where we're working is in chapter 6. And there's a long story here because, right, we're supposed to be doing reverse analysis of, say, 6 degree of freedom open loop manipulators. So it basically means given the constant mechanism parameters and then the desired position orientation of the end effector, what are the joint parameters to get you there? And we found that when we specify the desired position orientation, it's pretty much that transformation matrix 6 to fixed. Right, because we had the tool point thing, but we knew the tool point in the 6th, we knew the desired in the fixed, that all that whole story. And then what we did is once we were given the desired transformation 6 to fixed, so where the end effector is supposed to be, we made a couple of free choices so we could see an S7 line, and then we found the unique perpendicular back to S1, and we made a closed loop mechanism. Turns out that closed loop mechanism was 1 degree of freedom, and we knew theta 7, we ought to be able to solve it. And then we're not even like down the road yet because how are we going to come up with equations for that mechanism? Well, we made an equivalent spherical mechanism. So that's something kind of squirrely or new. And we found that because we translated all the S and A vectors over parallel, that any relations or equations we can get between the alphas and thetas for the equivalent spherical mechanism will be valid for the 3D mechanism. And remember, the 3D mechanism represented a reverse analysis problem. So it's a long story. And then we did kind of a crazy thing, is where we finished up just for the test, is we got this table here. I'm going to go ahead and hit full screen. And we just sort of did this exercise where we said, what if I was, I could look at, say, one of these spherical mechanisms and see my S vectors and my A vectors, and I could see the first coordinate system, Z along S1, X along A12. Could I express all these direction vectors in that coordinate system? And it wasn't any magic. Remember, we took S2 in the second, 0, 0, 1, and multiplied it by R2 to 1. and got, this was in the table here. And then we took S3 in the third and rotated it to the second and then to the first. And we had some weird patterns appear, and we introduced this notation, and then we took S4 in the fourth and brought it back to the third to the second, and all this crazy notation came out. And then what we finished up just for the exam was the terms over here. We took A12 in the first, which is, well, 100. We took A23 in the second, which was 100, and then pre-multiplied it by R2 to 1, and these patterns started to appear. And then we introduced this UVW notation. So we got all this crazy notation, and for doing that exercise, it doesn't help us to solve any problems yet, right? It's just, we did an exercise. So today we're going to try to start analyzing spherical mechanisms. And the one we're going to start with is this one. So I should have drawn some marks here to indicate that one of the links is fixed to ground. This is, the unit sphere, so you can see it out there. And I went ahead and took these three links. So again, I can see my S and my A vectors. So again, if there's S1 and S2, and here's the link I put in there, I sort of see that plane, and notice how A12 is perpendicular to that plane. And then we'll take a look at the other ones too. S2 and S3, and I can see the plane formed there, and A23 is perpendicular to that plane, and then the last one, the A31, is perpendicular there. So I can kind of visualize all this, and again, alpha 3-1 angle is nothing new. Put your thumb of your right hand along A31 and sweep from 3 to 1. And because it's a unit sphere, that the distance, if this was like a 1 meter radius, then the distance I would walk along that piece of metal would be r theta, so it would be 1 meter times alpha, would be alpha 3-1 meters. Okay, fine. So we've got this thing, but what's our problem statement? So here's what we're going to solve today. First thing is we looked at the mobility of this. So with this link being fixed, right, the mobility is 3 times n minus 1 minus each joint takes away 2 freedoms, and there's 3 joints. So if you look at the mobility, you get 0. So what that means is if I give you that parameter, that, and that, we don't need any other information in order to find these joint angles. So our goal for this mechanism is to develop, I call it a toolbox, a whole bunch of equations that have alphas and thetas in them. And then we're going to look at our problem statement and say, oh, hey, can I find an equation, for example, where theta 1 is the only unknown? If I can, yeah, great, I can solve it. So our goal is to generate these equations for this mobility 0 mechanism or a structure that's out here. Okay, so how are we going to do that? So I know the rotation relationship between 2 to 1, because remember on the 3D mechanism we said 2 is aligned with 1, we translated along the x by A12, and then we rotated alpha 12 about the x, and then we translated S2 along the z and rotated theta 2. So in the rotational sense, to get from the first to the second, let's go ahead and draw them. First coordinate system I'm going to do in red. Right, there's the z of the first, the x of the first is that way, and let's go with purple for the second. Z of the second, and x is along here. So if I think of 2 as aligned with 1, we're going to rotate alpha 12 about the x-axis. And then what's that going to do? Well, it's going to bring this red guy lined up over there. And then we're going to rotate theta 2 about the z. Because what's theta 2? Theta 2 is the angle. Put your thumb along Z2 and sweep from A12. It's going to take that red one and pull it over there. Right, so those 2 operations will take care of the orientation relationship. 2 is aligned with 1. We rotate about the x-axis by alpha 12, and then we rotate about the new z-axis by theta 2. And if we do that, as I erase all this junk here, we're going to get this. So I'm kind of not doing that because I'm getting lazy. But what if I want to get the relationship of 3 to 2? right? I could say 3 is aligned with 2 and rotate about the x, or I could add 1 to every one of these indices, which gets you the same result. And then we're in kind of a special thing here. In other words, I can go directly from 3. The third coordinate system has the z along here and the x along here. And I could say, imagine the first coordinate system is aligned with the third. I'm going to rotate alpha 3, 1 about the x, and then theta 3 about the z. And, oh, I'm sorry, was it theta 1 about the z? Yep, because I'm going 3 to 1. So again, 1 is aligned with 3. We're going to rotate alpha 3, 1 about the x, followed by theta 1 about the z, and that'll get you into the first. And if we did that, right, so this is 1 to 3. Or I took this and I added 1 to every indice, but I don't have, after 3, I don't have 4. 1 comes after 3, so you can see how 3, 1 came after. I added 1 to every indice, but there's no 4, right? It's 1. So if we did all those steps, all those rotation matrices, we would get, these 3. And I'm going to go ahead and transpose this one to get the relationship 3 to 1. So, okay. So, and again, I know what the physical meaning of this is, right? The column is x of 3 is seen in the first, the y of 3, if we need it. Okay. So now that I've got, these matrices written down, we're going to say, let's take S3 in the third, right, which I know is 0, 0, 1. And I'm going to bring it to the first coordinate system by going, to the second coordinate system. And we did that last week or sometime. And what we got was S3 in the third, in the first was, I think what we got in the notation was x2 bar, y2 bar, z2 bar. Okay. So we did that last time. We took S3 in the third and brought it to the second coordinate system, to the first coordinate system, and got that. But today, we're in this triangle. I can go direct. I know S3 in the third. What if I take R3 to 1? Oh, come on, computer. R3 to 1, S3 in the third. Right. I can do this because I'm in a triangle today, right? We're not in a 4-sided or 5-sided. We're in a triangle, so I know that relationship. So we are going to do this, and we're going to equate it to how we got S3 in the first when we went back to the second to the first. And we're going to start getting equations. Okay, so if we do this step that I just have in the purple here, I'm going to hit down because I think on the next page it's going to be a little cleaner. On the next page, let's erase that. Right, because here's R3 to 1. So if I take S3 in the third, I will get S3 in the first. Okay, S3 in the third is 0, 0, 1. So when I do row by column, we're going to go ahead and get that last column. I'm going to write it as S31, S1, S31, C1, and C31. Huh. So a couple days ago, we did, let's take S3 in the third and move it into the second coordinate system and then the first. And what we got on that, I'm going to write it in a different color here. And on that day, we got, x2 bar, y2 bar, z2 bar, if I haven't messed up. But because we're in this triangle, I can go direct third to first and get that result. So we're going to equate those, and we're going to get 3 equations. So trying to figure out where I'm going to write it now. Let's change it. Let's try green as a nice color. I'm going to get 3 equations. I'm going to have x2 bar is equal to S31 S1, y2 bar is equal to S31 C1, and z2 bar is equal to C31. Okay. This top one, it was going to be called the sine law for a spherical triangle. The second one is called the sine-cosine law for a spherical triangle. And the bottom one is the cosine law for a spherical triangle. So again, I go back to 1979, right? And I kind of wake up at this point and say, wait a minute. You told me last week that x2 bar and y2 bar and Z2 bar were SS negative SC plus, CSC, and then I ran out of room as why, CC minus SSC. And then we filled them in, the 2, and the 2. Oh, I'm going downhill, so 2, 3. My writing is getting terrible, but hopefully you're remembering, yeah, we did this. And then I got to 1, 2. Oh my goodness, I've got such a mess here. So I was like, hey, Dr. Duffy, you wrote this on the board, but last week you told me it was this. What is going on? Okay, here's what's going on. Put 3 marks over here. Those are those definitions of what those marks, those chalk marks represent. It just happens that because we're in a triangle, that S23, S2 just happens to equal that because we're in the triangle. So the definitions haven't changed at all. The only reason we have this is because those are laws for a triangle, and we're talking about a triangle. So I said, okay, so the definitions haven't changed. And again, in the book, I wish I would have put 3 marks there to kind of remind that, oh, that was the definition. So then I was like, okay. So I'm going to hit, oh, here, okay. So we took S3 in the third, and which is 0, 0, 1. And we brought it back from the second to the first, right? We had x2 bar y, and then we went direct and got that column, and then we equated them and got those equations. Well, we could have done that. We could have done it some other times. I could have taken S3 in the third, and imagine I brought it to the second coordinate system by going direct using R, 3 to 2. And then I could have gone to the second coordinate system in 2 steps. I could have taken S3 in the third, and I could have gone 3 to 1, and then 1 to 2. Or I could have gone direct. Let's go ahead and write it down. S3 in the second could have been written as S3 in the third and gone direct. Oops. 3 to 2. So if we do all that algebra, which is not hard, there's not any magic there, what we're going to wind up with is another set of sine, cosine, and cosine laws for this triangle. So now it's like, so I'm building my toolbox of equations. So now I've got 6 equations in my toolbox. Well, we could have taken S1 in the first. Oh, that one's not going to be very exciting, though. But no, we could have. Oh, no, it's okay. Let's take S1 in the first. And let me erase this red here. And so imagine I went ahead and calculated it in the second. Let's get rid of this red. Let's get rid of all of it, and then I can. So imagine we take S1 in the first, which is 0, 0, 1, and I bring it to the second. So S1 in the second would be R 1 to 2. Or I could have gotten S1 in the second by taking S1 in the first and gone the other way. So I would have an R1 to 3 and R3 to 2. And again, the 3 cancels. That's how I know I got it in the right order. And if I did all that, although I'm getting lazy because I'm not going to do all that on the board, you'd get another set of sine, cosine, and cosine laws. So now we got 9 equations, right? And then I could have taken S1 and gone to the third by going in 1 step. Oh, I'm going to cheat here, right? Go to the third in 1 step, or in 2 steps. Oh, no, that's a 1. 1 to 3. Oh, I've gotten it messed up here. In 2 steps, I've got to go 1 to 2, and then 2 to 3. Yep, and then the 2 cancels the 2. So basically, we took S3 and went to the first and got set, or we could have taken S3 and gone to the second. You got S1, I could go to the second, get 3 equations, take S1 and go to the third and get 3 equations. And I could take S2 and go get them in the third, take S2 and get them in the first. So it turns out that there's a total of 18 equations that we can get. And I'm kind of lazy to do the math today, so what we're going to do is show our toolbox. Right there. So the one that we proved was this set. Because remember how the X2 bar, Y2 bar, Z2 bar was the other day when we got S3 in the first? And then today we knew the R direct, 3 to 1 or 1 to 3, and that's what got us the right-hand side. So that's the one that we proved. I'm going to be lazy and just say, remember how you could take S3 to the second coordinate system. I don't know which one of these it would be. I should, but I don't off the top of my head. But again, there were 6 possible times. So we've got a pretty good set of equations here in our toolbox. So I'm going to hit down because I think I remember what's, oh yeah, we're going to go ahead and do this problem. We can solve this now for the toolbox that we have. So I went to the shop and got those 3 links made. So I've got alpha 3.1 was 135 degrees, and alpha 2.3 was 80 degrees, and alpha 1.2 was 120 degrees. So given for this spherical triangle, I'm going to go ahead and assemble this, and I want to find, you know, theta 1, theta 2, and theta 3. So we're actually going to solve a problem today, which is nice. Sometimes I get happy when I get back to numbers and realize, oh yeah, I can really do some stuff. So the first choice we have here is which one of those angles do we want to solve for first, and it doesn't matter. You could pick any one. I don't know which one I picked in the book, but I'm going to go ahead today and say, oh, for some strange reason, I decided I'm going to go for theta 3. So I'm going to look in the toolbox to say, can I find, it'd be nice, I can't guarantee it right now, it'd be nice, can I find an equation that has only theta 3 in it? If we can, right, then we've got a winner. And again, this is our strategy. What Dr. Duffy has done here is he built this toolbox of equations, and then when you get a problem, you dig through the toolbox to see if you can find something in there that's pretty useful. So we go back to our toolbox and say, I'd love to find an equation that only has theta 3. So I look at all the sine laws. Those are all the x's. They all have 2 thetas in them. So there's no way I'm going to find in that pile of tools that I'm going to find an equation that has only theta 3. And again, so what's nice about the notation, that 1 on the x tells us that when I expand that definition, theta 1's the only thing in there, the only theta. And then I look at all the sine cosine. The reason they're called sine cosine laws is because the sine cosine came out on the right-hand side. And again, I've got a theta there and a theta there. So no, I'm not guaranteed I'm going to find one, but with theta 3 is the only unknown. But I don't have a chance in though. So I go to the cosine laws and I'm looking and I'm like, ooh, yeah, right? So we got a chance. And you come down here and you say, oh yeah. And then remember how Z3 and Z3 bars definitions are identical. So it's like I got 2 of the same Phillips head screwdrivers in my toolbox. That's okay. So really, I walk out of this and say, it looks like I only got one choice. So sometimes one choice is okay, as long as it works, and it will work. So if I decide to go for theta 3 first, I'm going to go into that toolbox. And again, this is what we want you to be able to do. Is I got this problem, I got this toolbox, this is probably one of the most important things, is can I go into that toolbox and find an equation that's going to help me? So the equation, I can go with Z3 or Z3 bar, is Z3 equals C12. So I'm going to expand this definition. So it's CC minus SSC. Okay, it's going to have a 3 and a 2, 3 and a 1. Oh, a 3, 4 and a 2, 3. Huh, that's my only unknown, so I should be able to solve for that. So I'm going to get C3 is equal to C12 minus C23, C34 over S23, S34. So I'm trying to think of what software is going to be the nicest to do that in. I'll use MATLAB then for today. So we're going to go ahead and do the math. So and partly as I'm looking at the clock, and after we do the triangle, we're going to do the 4-sided one, and I would love to do the 4-sided one on Friday. Oh, did I mention though Friday I'm not going to be here again? It's going to be one of the, I should have said that for, I don't remember. I know I told Tiffany back there. I'm kind of in this mode where for family reasons and to maintain my sanity, I'm doing Monday, Tuesday, Wednesday here, and then when I get out of my 3 o'clock class, I drive 6 hours to near my grandkids, and I spend the weekend with them. Okay, so Friday's lecture will be on video. Okay, so we get rid of that. Now, I don't have MATLAB on my computer, but I have a program called Octave, which is a public domain. If you look up Octave and download it, it is, except for a couple of graphic things that I've had some issues with, Octave is MATLAB for free. Looks just like MATLAB. Okay, so I need to say, I'm going to say alpha, well, first of all, degree to radians. Let's see if I can make this bigger too, the text. Is there an edit? Is it under preferences? Oh, let me try one other thing. Let me try Control plus, you know, some of the standard Windows things. So is there a way to, is it under preferences maybe? I just want to see if I make the text bigger so you can all have a chance of seeing it. Workspace. Oh, wait. I saw a general. I thought I saw a font size. Which one? Oh, control and scroll the mouse. No, it's giving me equal signs. So it's not quite like totally Windows, because I bet you this works in Linux and all. So let's see, let me go back to preferences, and part of me is saying that the story was going to run out pretty soon. So oh, here we go, font size. Let's try 18. Of course, it'll probably change, and I'll never figure out how to change it back. Oh, apply? Oh, come on, give me anything. Now, in general, okay, so I think that's bigger. Is that big enough? Okay. How do you get pi in MATLAB? Just pi? Oh, okay. So degrees to radians is, oh, great. Is, I'm in degrees. Oh, what, pi over 180? Okay, radians to degrees is 1 over, so I need to have that. Okay, so then I'm looking at my alpha 3.1 is, what do we got here? 135 times degrees to radians. Alpha 2.3 is 80. And alpha 1.2 was 120. Okay, well, I'm going to go ahead and get like S12 is equal to sine of alpha 1.2 and C12, because we're going to need those. Okay, S23. And if you see any typos, you know, yell them out, because C23. It's funny, the typing is the one thing I took as a senior in high school that has really paid off, you know, so S31, I forgot the teacher's name, but I'm sure she's long gone right now, but I owe her a big thank you. Or maybe you owe her a thank you, because you'd be sitting here, and it would take us all period, and you'd be bored to death. Okay, so I think I got all those, and then I'm saying, gee, we took that Z3 bar equals C12, expanded everything, and solved for cosine 3, so I'm going to say cosine 3 is equal to C12 minus C23 times C34 divided by S23 times S34, and, oh, I did something stupid. Right, I expanded a Z3 bar as if there was a, but right, there's no 4, right? What comes after 3? 1. Now, if I was dishonest, I would have said I did that on purpose, because that way we all learned, you know, but no, I messed up. Okay, so I've got to change C3 is equal to C12 minus C2, oh, change them here too. C23, C31 divided by S23 times S31. And we got a number, negative, 0.5417. Okay. 5417, something like that. Yep. Now, I'm pretty happy it's between plus or minus 1, right? Because we're going to inverse cosine it. So to find theta 3, right? So theta 3, so I'm going to say theta 3 is equal to, what is it, ACOS? I forgot what MATLAB, because I got MATLAB and Python and C++ in my head, and I can't remember them all. Hey, here we go. Theta 3 degrees is equal to theta 3 times rad 2 degrees. So, yep.
For the equation for C3, I think the C12 should be the one that's being subtracted from.
Oh, because of this negative? Oh, you are right. Boom, boom, boom. Okay. So I use Maple. Right, when we solve for this, right, this could go to that side, this to that side. So thank you, thank you, thank you. Let's see. That goes over there. So it's going to be C23, C31 minus C12, which should just take care of the negative sign. So let's go ahead and do that. So I'm going to cheat and say negative theta 3. And theta 3 degrees equals negative theta 3 degrees. Okay. Oh, no, let's not do that. What did I mess up there? Theta 3. Let me redo it. C3 equals C23, C31 minus C12 divided by S23 times S31. Okay, and then theta 3 is ACOS. The reason I'm pausing is it shouldn't that have been the negative of what I had before? Oh. What did I got wrong here? So I'm looking at this line up here, and then this line here, and I expected the answer to be the negative, and look at I got that. Oh, I did get the negative, but what happened when I did inverse cosine? Oh, well, let's go with it. Let's go with it. Theta 3 times rad 2 degrees, 57. Okay. So I'm going to say I did get the negative of cosine theta 3 like I expected, but when I did a cosine, it's a bit different than what I expected, but that's okay. So at this point, we're saying we've done pretty good. Given these alphas, boom, I decided to go for theta 3 first. We looked in the toolbox and got that. I messed it up twice and and then we did the inverse cosine. It said that theta 3 was, what did we have there? In degrees, 57 point, and the arrow's right in the way, 0.201.
So I think it's because they're both, like one's 57 degrees away from 0, and then the other is 57
Over from 180,
from
yeah. So I think we're going to be okay. But I'm pretending the first one didn't happen. That was a mess up. So if this is correct, and at this point, we're doing pretty good, right? We're going to declare victory. I'd say, what are the corresponding values for theta 1 and theta 2? But we have to stop here because when I went to the toolbox, all I could get was the cosine of theta 3, and I could look through the toolbox. There's no way I can get the sine of theta 3, right? If I knew the sine and cosine, then there would be one value of theta 3. If I only know the cosine, there's two values of theta 3, and our calculator or Octave gave us one of the answers. So we had the cosine of theta 3 was about here, 0.5417. And it came out and said 57.201. So the inverse cosine gives you the value between like 0 and 180. But there's another answer out there. So I'm going to call this theta 3a. Because if all I know is the cosine, when I go to assemble those three links and I look at those theta values, there's two ways to assemble it. One way would be to assemble it where I made the theta 3 equal to 57.201, and the other one would be 360 minus that. Right? So that's another valid angle, you know, that's between 0 and 360 that does have a cosine of that. So that angle would be, I can't do the math here. That minus 57 would be about 303. So it's probably going to be about 302.8 about. So this is telling me from our toolbox that there's going to be two ways to assemble those three links. There's going to be two triangles. And I'm going to skip down to the picture to show you those two triangles so that you're not kind of panicked about it. But here's the two ways of putting those pieces of metal together. Oh, look at that, matched our calculations. Oh, yeah, that was the other. Oh, what am I doing here? I can't believe I've had this typo for years on this slide. That should have been the B case. So again, in these pictures, I've got, this is my fixed link apparently. And again, the angle between the planes, right? There's a plane here and a plane there. The angle between the planes is the same as the angle between the normal to the planes. Normal to the planes are the A vectors. So I could have drawn theta 3, right? Put your thumb along S3 and sweep from one of the A's to the other. But I drew it here as if it was the angle between the planes, those, like the plane here and the plane here. I put the theta up there. So here's the case where we drew it where the theta was 57.2. And then here's the case where the theta was measured. Again, you put your thumb along S3 and sweep from A23 to A31, which are not drawn here, but you would get this 302-degree type case. And if you go back to planar mechanisms, so imagine I had a link and a link and a link. I could put those together like this, or I could put those together like that. So if I had those three flat pieces of metal, so this is like this board is like a spherical mechanism where the radius is infinity, right? Because it's flat. So there's a between the planar stuff and the spherical mechanisms, there's kind of a connection. So if I had three flat pieces of metal in the plane, and I fixed that link, there's two ways of putting it together, because there's this angle or there's that angle. And the same on the other angles. So I'm not really that surprised that there's two ways of putting this triangle together with these alphas. So here's our two values for the thetas. So now when we go, and I'm going to do it on this picture. So let's see, we got theta 3, so that's this angle. So it's kind of awkward on this picture, that angle there. So I took this link, alpha 23 was, and this was all drawn to scale too. I think that was 80 degrees, and this one was 135. And I went ahead and I set that angle. Okay, when I go ahead and assemble this and put this last link on there, I expect to get a unique corresponding angle for the theta 1 and 2. So what I mean is once I set this A case and I take those two red pieces and I lock them in, I don't expect there to be two answers for theta 1A for the A case. So what it's telling me is I expect to go in the toolbox now and say for the A case where theta 3A is 57.2, I expect to go in the toolbox and get the sine and cosine of theta 1 for that A case. And I expect to go in the toolbox and find equations that'll give me the sine and cosine for theta 2 for the A case. Okay, then I'm going to go down here and take the B case, the 302 number. And okay, I've positioned these, and again, for that B case, oh man, I can't believe that I've done that and left it there for so many years. But I expect to be able to get the sine and cosine for the theta 2 that goes with the B case, because there's only one answer there. I put it together, and theta 2b can't have two values. And then the same over there, I expect to get the sine and cosine. So we're going to kind of go into the toolbox with that expectation. I just want to see if, oh, good. Dink. Dink. Now I have to remember to upload this to the website, but I wouldn't have slept leaving that an A. It's been an A for like 20 years probably, right? Okay, let's go back to the toolbox. You say, you know, we used that equation, which was the same as that equation. That's how we got theta 3. Oh, and I can even sort of draw I've got this A case, theta 3A, and I've got theta 3B, and I know the values, right? 57.2 and 202 point something, 302 point something. And I go in the toolbox and I say, you know, I want to get the corresponding value of, again, for the A case, I'd love to get theta 1A. So I want to get the sine and cosine of theta 1. And I'm looking around, and there's a lot of options. In other words, I want to find an equation that, well, there's not that many good options. But I'm in the toolbox and said, you know, I'm looking for an equation. It's okay to have theta 3 in it because I just got theta 3. I solved it for the A case and then the B case. So it's okay to have an equation with theta 3 in it. I'd love to find an equation that also had theta 1 in it, because that's who I'm looking for now. And I look around, and I look around, and I look around, and I go, oh, wow, look at that. And oh, my goodness, look at that, sine and cosine. Part of me is wishing I did this in Maple now instead of Octave, because I know Maple better, and I would have done a better job. But we are ready to solve for the corresponding value of theta 1. We're going to go into the toolbox, and we're going to say, I'll get rid of this. We're going to say, wow, in the toolbox, I sure like that equation. You know, S1 is equal to X3 over the sine alpha 1, 2, and C1 is equal to Y3 over the sine of 1, 2, where that guy's definition is, let's see, oh, there's no bar on it, so I'm going uphill, so I get to 2, 3 before I get to it. And this guy's definition is negative SC plus CSC. And I'm going uphill. And I get to 3, 1 after I get to, so I didn't do the 3, 4 thing today, or again. And then I look at the, you know, the right-hand side here, and I'm going to take the A case. So I'm going to say the sine of theta 1 for the A case is, let's just go ahead and put it there. For that, I'm going to take the A case, theta 3 that we've got. And for the A case, let's see, negative, I'm going to put the A case for theta 3 in there, and then we had, what, 2, 3, 3, 1. So let's go ahead and I know everything on the right-hand side, right, for the A case. So we're going to get the sine and cosine for the A case. Knowing the sine and cosine, I know the unique theta 1 for the A case that goes with theta 3A. So let's go ahead and do that. Hope I don't mess this up terrible. So I'm going to say that sine 1 A case is equal to, and then I'm worried about my, here we go. Let's go ahead and get the sine and cosine of theta 3, the A case. So that's the sine of theta 3. Okay. The cosine 3, now for the A case, is just the cosine of theta 3. Okay, what about the B case? Right, it's got to be the sine, and then I could go 360 minus theta 3A. Right, but if I take any angle, I add and subtract 360, I get this. So what if I take this and I subtract 3? So basically, the other theta 3b is going to be the negative of theta 3a. So I'm just going to do it that way. Negative theta 3. And C3b case is the cosine of negative theta. Okay, so I got the sines and cosines of theta 3 for the A and the B case, and now we can go ahead and say sine theta 1 in the A case is S23 times S3A divided by S12. A, it's between 0 and 1, so I'm happy about that. Cosine 1A is, let's see, negative S31 times C23 plus C31 times S23 times cosine 3A divided by S12. Boy, I wonder if S1A, is that how they do it? You know, I'm going to square and add these, and boy, they better equal 1. Right? I mean, like almost for all the stuff we did, what were the odds that that was, well, it better happen, and it did. So our toolbox has got valid equations, so everything is hunky-dory. Okay, so now I'll say theta 1, and this is the A case, is A tan 2, S1A, C1A. Okay, theta 1A degrees is equal to theta 1A times rad 2 degrees. So I got 72.915, and I'm going to go to the who's a who here. Hey, hallelujah. I don't have any other typos. Okay, so now I know for that value of theta 3, we went ahead and built that, and then when we assembled the triangle, and everything is drawn to scale here, so that is 72.92. If I can get this all to erase now. So life's looking pretty good. Let's go ahead and do the B case while we've got it there. The B case is going to be, right, for the B case, I'm going to take the same, what was the x2, y2 equations, and I'm going to say that for the B case, and then for the B case, the sine and cosine of theta 1. And then I kind of look at it and say, you know, here's theta A and here's theta 3A. I'm trying to look at this and just save some math mistakes, but right, the cosine for the A and the B case are going to be the same, right? Because remember, the first equation we had was we went for theta 3 and we got cosine 3, and all we knew was cosine. So I don't have to, you know, the B case is going to be the same as the A case. So I'm trying to save a little bit of typing. Okay. C1A, what do I not have there? Oh, I got it the wrong way. C1B, right? Is this going to be the same as that? And then I look at this equation, and if I look at the sine curve, let's see, so we had a theta 57, and the other is this. Oh, those sine values are going to be the negative of each other, so I expect when I evaluate this for the B case, S1B is going to be the negative of S1A. So I'm just trying to save a little bit of, this is a negative. And then I can say theta 1 B case is equal to A tan 2 sine of the B case, cosine of the B case. Theta 1 B degrees is theta 1 B times rad 2 degrees, negative 72.9, well, let's add 360 to that. 360 plus, because it's the same, theta 1b degree, 287, because what I'm thinking is, yeah, when I went to that slide, I was going to see the 287. So again, when we tackled this problem, we said, well, I decided to go for theta 3 first. If that's the case, I went in the toolbox and I found that Z3 equation, which got me cosine 3, which means there were two values of theta 3. When I go back in now to get the corresponding theta 1 and theta 2, I really expect to get the sine and cosine of those angles. So for the A case, I'll have the unique theta 1A that went with theta 3A, and then I'll get the unique theta 1B that went with theta 3B. And we've got 1 minute left on the clock, but we got one angle left to go is theta 2. So we're going to go into the toolbox and hit the highlight here and say, again, it's okay if I have theta 3 in the equation because I've got that, the A and B case. It's okay if theta 2 is in. It's actually okay if theta 1 is in there now because I got, so I got a whole bunch of possibilities. But when I dig in here, I kind of like these two. Because remember, we're trying to get the sine and cosine of theta 2, and there they are. So again, what I'll do is I'll expand that definition. I'll put theta 3a into this and into this. For the A case, I'm going to know the sine and cosine theta 2. Then I'm going to take those same two equations. I'm going to take the B case and get a new number and a new number. For the B case, I know the sine and cosine, and you tan to that. And yeah. So it's not super exciting while we solved a triangle, but we're really careful. For those three pieces of metal, there were two ways of putting them together. So in both of these pictures, I locked that one down. I did not draw the A vectors though, but I did indicate the thetas as the angle between the planes instead of the angle between the normals to the planes. And those are the two cases that came out. Okay, so what we're going to do next is, we got one more story to tell. We're not even done with the triangle, but that's okay. That's okay. So we did a lot today. We generated this part. There's a little bit more going to go in the toolbox for the triangle. There's a little more that's going to go in there, but we've got 18, is that right? 1, 2, 3, yeah. Equations that I don't have to prove every time. I just get my toolbox out and I know these equations are valid. And then I look at my problem. What am I given and who am I looking for? Maybe I can find one equation, one unknown, and we did today. So that's kind of our approach. Build the toolbox, and then there's a little bit more we're going to throw in the toolbox for the triangle, and then we're going to do the 4-bar after that. So, and again, Friday will be just a video on the website instead of the classroom setup. Okay, shall see you then.